I want to also take the opportunity to thank all the organizers, Kara, Chaba, and also Gergo for putting together this very wonderful seminar. And to be honest, this is sort of the most regular activity I had in the past few weeks, besides having lunch and dinner, and really learned a great deal from the seminar series, and thanks a lot. So before I kick it off, I want to share this famous quote by Albert Einstein, which I like a lot. And he says that the mere formulation of a problem is far more essential than its solution. And to regard old problems from a new angle oftentimes requires creative imaginations and makes real advances. And in this lecture, or in this talk, I hope that I can convince you that we can bring in some new perspectives from dynamic systems when revisiting some of those classical reinforcement learning algorithms, and hopefully bring some new insights of these algorithms. And the majority of this talk will be based on the work with my former postdoc, Donghwan Lee, who is currently an assistant professor at KAIST University. And I think right now is after midnight at South Korea. That's why he wouldn't be able to attend the seminar and answer some of the questions in the chat box. But if you have any other questions, just feel free to speak up or interrupt me at any time. So if there is additional time, I would like to also introduce some of our very recent results on double Q learning. And this also aligns with this whole dynamic system perspective, and also aligns a lot with Aditya's talk that was given 2 weeks ago. And this is joint work with Wentao and Harsh, as well as my colleague Srikant at UIUC. So since this is the reinforcement learning seminar, I guess I don't need to go through the baby introduction about what is the reinforcement learning, but just to set up the stage and make sure we're all on the same page. So throughout this talk, I'm going to look at infinite horizon discounted MDP problems, and I'm going to use S as the state, A as action, P as probability transition matrix, R as reward function, and gamma as the discount factor, which is between 0 and 1. I'm going to consider policies that are mappings from state to action spaces, which are deterministic mappings. So we all know that there are two fundamental tasks in reinforcement learning. One is the policy evaluation, and the other one is the policy optimization. And both of these can be essentially solved through Bellman equations. And in fact, a lot of the classical reinforcement learning algorithms are designed to solve these Bellman equations based on some stochastic dynamic programming. And there are several key challenges of solving these Bellman equations that we all are familiar with. First of all, oftentimes we don't know the underlying dynamics, and we have to resort to some stochastic approximation schemes, such as the Q-learning algorithm. And also, a lot of times the state and action space can be very large, and we have to resort to function approximation techniques. However, it is also known that even for the classical Q-learning algorithms could potentially diverge when linear function approximations are used. And this also leads to the very infamous name called the Deadly Triad. And in this talk, I'm not trying to break this curse of the Deadly Triad, but rather trying to build a better understanding of the classical reinforcement learning algorithms. And I have always been very fascinated about this whole close interplay between dynamic systems and reinforcement learning. So on the one hand, we know that RL is all about the learning of unknown dynamic systems. On the other hand, a lot of the RL algorithms themselves can be viewed as discrete time dynamic systems, and they can be analyzed through dynamic systems. And as a result, a common recipe, I would say, for analyzing many of the classical reinforcement learning algorithms really hinges upon either stochastic approximation schemes or the associated O.D.Es or dynamic systems. And I would say typical results or the existing theoretical guarantees people have come up with really can be divided into three main categories. So the most common results we see in the literature are asymptotical convergence of those classical algorithms, such as TD learning or Q-learning, and many other variants. Very recently, there has been a line of very exciting work that provides finite time analysis and convergence rate for some of these algorithms. And more recently, I think driven by the work by Shom and also Aditya, there has been lots of some recent work that tries to give even tighter error bounds for these algorithms and to characterize their exact behaviors. And here, I'm using orange color to denote all of those references that usually is arguments based on dynamic systems and using those blue references, colored for references that uses purely stochastic approximation arguments. And I have to say that this list is by no means exhaustive, especially given that there are so many archive papers are coming out in the past 2 weeks after New York's deadline. I'm sure I'm missing a lot of them here. But you get the idea here, as you can see, that the majority of the result, I think, really relies on this whole point perspective dynamic systems, as you see those orange references there. And a lot of those stochastic approximation-based arguments, I think those are heavily rely on case-by-case analysis and sometimes are very unintuitive to understand to some extent. On the other hand, and the work that I'm going to present today basically falls under this whole umbrella of dynamic system analysis here.
Niao, there's a quick question. I think that it can be answered quickly. The question comes from the audience, and the question was whether, like, so what's the difference between these two types of analysis in a nutshell?
So the dynamic systems, I think a lot of those focuses on looking at this continuous time dynamics and look at the symptotic stability of those O.D.Es, whereas the purely stochastic approximation schemes, in my understanding, those looks more in the discrete time analysis, like the discrete time system.
They never make the passage to the continuous time formulation.
Right, yeah. You don't necessarily need to pass on to the O.D.Es. You just
directly analyze the discrete time.
Right.
Updates.
Right. Yeah. So on the other hand, I would say there is also a lot of recent reinforcement learning algorithms that are based on completely different perspective, like the optimization perspective, or based on some optimization framework. And a lot of these algorithms start with proposing some sort of objectives. Say, for instance, you want to minimize the projected Bellman errors, or you want to solve a zero-sum game between the actor and the critic. And then we can basically apply a lot of the existing first-order methods like stochastic gradient descent or primal dual algorithms to solve these optimization problems and derive some algorithms for reinforcement learning. And typical examples, say, for instance, in policy evaluation, there's gradient TD algorithms and a lot of recent variance-reduced variants of those algorithms that tries to minimize the projected Bellman error. And in policy optimization, there could be all kinds of different objectives, either to maximize the long-term reward or just to play, like to solve a zero-sum two-player game between the actor and the critic. And I would say a key advantage of this, and I think Shai last week, he also talked a lot about this TRPO, which is essentially based on mirror descent algorithm. And I think a key advantage of many of these optimization-based RL algorithms is that when it comes to the analysis, it's fairly easy to obtain not only asymptotic convergence, but also like a lot of those, we can easily obtain finite time convergence rate for these algorithms by leveraging existing optimization theory. And also it's much easier to cope with nonlinear function approximations, and still we will be able to get some sort of theoretical guarantees even there. So in contrast to sort of comparing to this optimization perspective, I would say there are some still unique strengths with this dynamic system perspective. First of all, I think as we can see that a lot of the analysis can be fairly general, especially if those are based on continuous time dynamic systems. So those applies to a wide range of stochastic approximation schemes and algorithms. And in a lot of these algorithms, we don't necessarily need to construct what is the objective, what are the gradients, or how we should come up with some regularization terms. Those are basically objective-free algorithms. And I would say one of the very interesting points as also discussing some of the earlier talks is that it provides a way to build exact characterization of the behaviors or the underlying dynamics of the algorithms so that we have like exact performance of those algorithms rather than just some upper bounds of those algorithms. And I think those are particularly useful to guide some of the practical implementations of these algorithms, which I will also discuss a little bit more later in the second part. But this type of dynamic system approach also comes with challenges, particularly we know that even for the simplest Q-learning algorithm, the underlying dynamics are oftentimes nonlinear, and it's extremely challenging to analyze I would say very challenging, and also case-by-case, requires case-by-case analysis for the stability result for those nonlinear systems, especially if we have nonlinear function approximation involved. So one of the questions that I'm trying to answer here in this talk is really how can we systematically analyze some of the nonlinear dynamics for this very large family of Q-learning algorithms or potentially other RL algorithms. And the idea basically comes back to essentially something we call based on switching systems. And before we proceed, I want to maybe just give a very quick refresher on the O.D.E method that has been widely used, maybe not widely used, but I think it's a very powerful tool for sure. And this is largely popularized by this seminal work by Bokar and Schwarman that was published in year 2000. And I think since then, this has been rated as the top 20 most influential papers on SIAM journal on control and optimization. And I'm sure many of you are familiar with the key idea of O.D.E method. So basically, we can analyze the convergence of any discrete time stochastic approximation algorithm by tracking the associated continuous time O.D.E. So if we are able to show that the underlying sort of O.D.E is asymptotically stable, then that guarantees the convergence of this stochastic approximation algorithm. And here I say the system is globally asymptotically stable if it converges to an equilibrium point for any initial condition. Okay. And to be more specific, we have probably seen this theorem many times, like by Bokar and mine in 2000, and which basically says under the following conditions, right, A to E, that we can show that the algorithm or the stochastic approximation will converge with probability 1. And a lot of those are just basic assumptions, which you can easily verify, like the Lipschitz continuity of the mapping or the non-square summable step size, and as well as like bounded noise of the martingale differences. The critical two assumptions or conditions are the asymptotic stability of the limiting O.D.E and the stability of the original O.D.E. So basically, this algorithm is this theory is fairly general, right? As long as we can show, and it's also particularly useful, right? As long as we can show that those O.D.Es are asymptotically stable, then this immediately leads to the convergence of stochastic approximation algorithms. And I should say that oftentimes those two stability results comes hand in hand, and if you prove one of them, you can easily prove the other one of it as well. And the widely studied case in the literature is a case where we have linear systems, and it's well known that a linear system is asymptotically stable if and only if this matrix A is Hurwitz. And this has been widely used to analyze TD learning and many of the variants of TD learning algorithms. So for instance, if we look at TD learning with linear function approximation, you can easily write down what is associated O.D.E, which is exactly a linear system. And this matrix A can be easily proven to be a Hurwitz matrix. And this analysis has also been, as I said, applied to many other TD learning variants, and also to some Q-learning variants if we use some of those linearization techniques. However, in general, like a lot of the reinforcement learning algorithms, like Q-learning algorithms, are not necessarily corresponding to a linear system. So oftentimes those could be a fairly general nonlinear system, and those mapping is not even necessarily to be differentiable because of the max operator. So the stability of nonlinear system has actually been widely studied, I think extensively studied in the literature, and here's just a sample of textbook result. So which says if there exists some Neapolov functions that satisfy certain conditions, then you can show that indeed those nonlinear system is asymptotically stable. And one should know that this is only a sufficient condition, and in practice, although this is a very general result, it could be very challenging to construct this type of Neapolov function. And this type of idea has indeed been applied to some variant of Q-learning algorithms in the literature. So of particular, and I would say that when there exists some special structure of nonlinear systems, the story could be much nicer than this one, right? Of particular interest is a class of linear switching systems. And here, what do we mean by linear switching systems is really just a system as follows, right? This is very similar to linear system, except that this matrix A is not fixed, but rather this A can be switched among a connection of matrices. And this is essentially controlled by some switching signal sigma, which is denoted as sigma t. And this switching signal can be arbitrary signal, or it can be just controlled by some state feedback policies, which depends only on your state xt. Okay, and in this case, we call it state feedback switching signal. And this type of switching systems has indeed also been extensively studied in the control literature in the past 2 decades, I would say. And a typical result, what people come up with is that, so there exist also sufficient and necessary conditions to verify the stability of this linear switching system, particularly if we can find a full rank matrix L and a family of negative row dominant diagonal matrices A1 to AN. And if those matrices satisfy this equation here, then that implies that the original system is going to be asymptotically stable. So I should also mention that this is closely related to the robust stability of uncertain linear systems, but let's not go into too much of the details there.
I do have a question. So maybe I just missed it. What's the assumption? Okay, so there is the sigma function can be arbitrary. Like, what is if it's just a constant? Then you don't really need this as a necessary condition, right? So some range condition for sigma is necessary or something?
Sigmoid. So here is sigma. Yeah. So it's just a arbitrary function.
If that function assigns the same number, let's say 1, no matter what xt is, do I really need this necessary condition? Which says that for all sigma, there has to be this thing. Maybe I just don't understand this necessary condition, but.
So this result holds true for arbitrary switching signals. If your switching signal has very special structure, and let's say it just is deterministic and always assigns to just one.
But it that this is a necessary condition, like what I see below. And I'm wondering about whether this is really necessary if you're not really switching in that sense, right? Like then.
Yeah, I would say this is necessary for the case where you have arbitrary switching, but if you have particular...
I choose the worst case sigma. Okay.
Yeah, it's a worst case, yes.
I see.
That's sort of related to the robust stability when you have sort of an uncertain A.
Yeah, okay. So if you want this to be globally asymptotically stable for any choice of sigma, then this is a sufficient and necessary condition. Makes sense.
Right.
Thanks.
Yes, this is fairly strong, as you can see, that if you have like special thing, like it's always the same matrix, then you have much sort of tighter conditions, like just the Hurwitz matrix would be sufficient. Right, that's a very good question. Yes, I should make it clear. Yes, this holds true for arbitrary switching signals. And now we're ready to see how those switching systems are actually related to Q-learning algorithms. And I think the connection is actually quite natural. And let me just start with the standard Q-learning algorithm for simplicity, and we'll move on to other variants later on. So here is indeed the asynchronous version of Q-learning, where at every iteration, just a random sample of state and action pair is updated. And from like textbook result, we know that if every state action pair is visited infinitely often, then this will converge to the optimal Q function with probability 1. And this analysis and actually this convergence result has been already established and proved using several different approaches. And I think the one based on stochastic approximation argument is first established by Tsikas in 1994. And I think more than 20 years ago, Chaba gave the very first convergence rate analysis for this algorithm. And this has been recently improved. I think those are very recent results with very sharp bounds of those convergence rate, with sharp, I think, dependence on the state action, the size of state actions, and also the mixing times. And particularly, I think this last work that was published, I think, less than 2 weeks ago, gives the state-of-the-art bounds for those rates, and which I will not go into detail here. And in this talk, we will mainly focus on a special O.D.E treatment of Q-learning algorithms, and we don't care about the convergence rate for now. So if we just look at this Q-learning algorithm and we write down what is the associated O.D.E, so this is what you will immediately get as the O.D.E here and in the vector form. And just to go through maybe a couple of notations here, D is just a diagonal matrix corresponding to the state action distribution. And this P is some concatenated transition probability matrix. And this small pi here is the greedy policy, which depends on sort of the Q function here. And this capital pi is just some 0, 1 matrix that depends on your policy pi. Okay. So if you look at it carefully, you will immediately see that this is nothing but just an affine switching system. Right, this matrix A here essentially is just controlled by your greedy policy, right? So this is, and your your greedy policy basically only depends on your value of your QT, right? So this is essentially just a state feedback policy here, switching signal here. So this is exactly just an affine switching system, and I put an affine here is because we also have this affine term here, which also depends on the same switching signal, sigma. And as we discussed earlier, so if we're able to show the asymptotic stability of this switching system, then we're done, right? Then we can essentially just establish convergence of Q-learning algorithm. So there is a small gap, as you can see, that between this switching system and the original linear switching system we discussed before, due to this affine term. And this is what makes the analysis a little bit more, I think, a little bit tricky here. So in order to deal with this affine term and to just apply existing theory, so what we come up with a very simple solution to this by essentially just sandwiching the current switching system with 2 simpler systems. So we constructed an upper comparison system by simply removing or ignoring this affine term here. So you can see that this upper comparison system is simply just a linear switching system without any affine term. Okay. We can also construct a lower comparison system where we simply replace this greedy policy by the optimal policy, pi of Q star. So you see that this system here is just a simple linear system without even any switching signals here. So, and based on sort of the definition of the greedy policy, we can easily show that this mapping here is indeed lower bounds this original mapping. And this mapping here actually upper bounds the mapping here, which you can easily prove based on just the definition of greedy policy. So now the rest is basically straightforward, as you can imagine, right? So the lower comparison system is a linear system, which we already know perfectly what is the stability of that, right? If the corresponding matrix is Hurwitz, then this means that it's asymptotically stable. And the upper comparison system, also we know perfectly what is the stability of that. So in fact, we can easily show that those matrices, A sigma, are strictly negative row dominating diagonal matrices. And that means you can easily verify that stability condition we need, or that sufficient condition we need for building up the stability for linear switching systems. And once we have the stability of those 2 results, we can immediately basically get the stability for this original switching system. And this is guaranteed by the so-called vector comparison principle, which says that if you have a mapping F bar that upper bounds the mapping F here, and if your initial point is also upper bounds the initial point here, and if further you know F bar is also some sort of quasi-monotone increasing function, then you can show that the whole state trajectory of this system will upper bound the state trajectory of this system here. So as you can see that the proof is fairly straightforward. Literally, you just have to verify that those matrices you get from the ODEs are strictly negative row dominating matrices, and your function f here is Lipschitz continuous and quasi-monotone, then you are done. So that basically leads to essentially the immediate conclusion we have is that assume that your step size satisfies this Robbins-Monroe step size, then the Q-learning algorithm will converge with probability 1. And this analysis indeed can be easily extended to many other Q-learning variants as well, which I will discuss in a bit and see if you have any questions for now.
Yeah, I do. So are you going to elaborate on why these conditions are met? Like why these are lower and upper bounds? And like, yeah, I guess like if you did a lot of calculations with this thing, then you can work it out for your own sake. But maybe a few words about like why these inequalities hold would be useful to have.
Why would it be useful to have those upper and
yeah, like can you explain like why these inequalities hold?
Yes. So the inequality holds if you look at this term here, right? So this is sort of the policy for the Q function at t, right? This is optimal policy. So you see that under like if or maybe let's just look at
the
this
optimal
one.
policy is greedy with respect to Q star, and all the other policies are suboptimal.
Right. Then you need
and
to this
non-negativity of P. Right, so that it's a stochastic operator, and then that's it.
Yes, that's it. Yeah. So
okay, so that's the upper bound. How about the lower bound?
So the lower bound is also the similar story there.
Okay, but it's a slightly different story, right? Like somehow yeah, some part of the story overlaps, but maybe it's worth just saying what it is.
So the lower bound here is we're using the optimal policy Q star, right? So this policy is not going to be optimal corresponding to QT, right? So this part is strictly less than that part. Like when you use the greedy policy for QT, right?
Okay, okay. How about the other term?
So the other term is because like here is Q star. So when you so when you use greedy policy for like the optimal policy is this term is going to be greater than when you use a greedy policy for QT, right? Because it's not optimal corresponding to Q star.
Right. Okay. A question from audience. Pi of Q star is the same as pi star?
Yes. Yes. Yeah.
Okay.
That's true. I'm just this is a bad notation. Actually, it's pi Q star. Yes.
Okay. Aditya is asking, are we going to ensure that we're visiting all state action pairs like infinitely often, or that's not a concern here?
Can you repeat the question?
Yeah, like usually for these algorithms to converge, you need to ensure sufficient exploration that you're visiting all state action pairs infinitely often. So the question was like, are we going to look into that, or like, is this something that's taken for granted here, or what's going on?
So the step size here is basically just a Robbins-Monroe step size, where like you have this it's square summable but non-summable like step sizes, which is sort of the only condition you need to apply the Bocart's lemma, right?
So in the analysis, because this is asynchronous stochastic approximation in Fitzsimmons proof, there is also an implicit assumption that each state action pair gets visited infinitely often.
But here the step sizes are not specific to the state action pairs. I think that there is a global step size, and so the state similarity. So you're assuming that like there is a Markov chain that's like you're driving a Markov chain, and that's how the state action pairs are generated, or is it the IID model? Which one?
So for simplicity, we assume the IID model, but that can be easily extended to the Markov assumption. And as you just mentioned, the step size here is not dependent on the state action pairs, right? Those are just global step sizes. And you can just set those to, we'll say, 1/k, right, for simplicity. And this is also kind of one of the key difference between our analysis to the existing analysis. I think the existing analysis often requires like state dependent step sizes, but here those are just
Sean can come in, but I think that, I don't know, Borker and Sean, like they had a result which was somewhat similar in that they use a global step size. But
yeah, I suppose the real question here is like, how are the actions being generated? Like, what is the behavior policy that generates the actions? Is it like a greedy policy, an epsilon greedy policy, or just some fixed policy? I guess this is what
I guess that's not a, yeah. So that's out of the scope of the method, right?
No, I think because we're looking at the sort of the symptotic performance. So essentially, I think of the samples should follow sort of a stationary distribution.
Right. So it's a fixed policy, essentially. Yeah.
There is a fixed policy, yes, but you can relax that. Like, say, for instance, you can use a time varying policy, and as long as those policies will converge to some extent, right, and then they still apply.
All right. Okay. Gotcha.
Yeah, I would say all of those sort of tiny details can be relaxed with some complications of the analysis. So here I'm showing you the very basic version of it.
All right, gotcha. All right.
That's a very good question. Yeah, thank you for pointing that out. So now I think
I have a quick question, if I may ask. So when you write the O.D.E, you're switching. So you have the discrete system and you go to the O.D.E. The O.D.E is in continuous time, which means your policy is changing continuously and you're switching continuously. Can you still use the result that you showed earlier? Because there you switch only between m different matrices, right?
So this is because it's a finite action, right? So the number of policy you have is because this deterministic policy is finite.
Got it. Okay, thanks.
That's a very good question. Yeah, thank you for clarifying. Yeah, pointing that out. Yes.
If we want to, yeah, like, okay, so there is a question from Amir Masood. He's asking whether you can somehow augment the state space and transform the affine system to a linear system by that and avoid the analysis with switching. I don't know how that would work. Maybe it's a hybrid kind of approach. Amir Masood, if you have a microphone, maybe you can ask your question because I'm not sure I understand it.
Oh, hi. Yes, sure. Well, this is just the idea, but I guess we have a fine dynamical system. I think probably we can just extend the state space, like add a copy of the same state space and then transform that affine term or into some part of the dynamical system that doesn't have any dynamics essentially, but only has initial condition, and that value stayed the same for the whole time. And I think, I don't know if the whole system can still be shown that the same condition would be satisfied or not. But I think it is possible to transform a fine dynamical system to a linear dynamical system by augmenting the state space.
I think that's actually a very interesting idea, and I think that's possibly true. And what we're doing here is something slightly different. Is we're just trying to using existing theories without having to augment the states and transforming it into linear systems first. So, but I think that could be an alternative way to establish the stability for affine systems for sure. Yeah.
Okay. Right. Thank you.
Okay, so maybe I'll move on to some of the extensions we did. First of that is for target-based Q-learning algorithms. So this is essentially motivated by the ideas of double Q-learning and deep Q-learning, where people introduce this target networks in order for estimating the target values in order to reduce the overestimation bias. And there are many ways that actually we can try to update the target networks or target parameters. Say, for instance, we can update those through a Polyarc averaging fashion. That's what we call averaging Q-learning. Or we can update symmetrically. That's like the original double Q-learning. Or we can update it like periodically, and that's corresponding to a periodic Q-learning algorithm. So we can also translate all of those to like a TD learning setting and get a bunch of different target-based TD learning variations. Those are some of our earlier work. And here I'm going to show you that actually if you look at, say, for instance, the averaging Q-learning algorithm, so this is like, so the algorithm is simply given as follows, right? So we're using this estimator, a separate estimator QB to estimate these target values, and we're updating QB based on this Polyarc averaging iteration. And we can immediately show that this is also an affine switching system based on similar argument as before. And we can also easily show that indeed this converges with probability 1 under just the same sort of step size choices and same assumptions. So nothing is really so this doesn't really require any extra efforts to show this type of result. So similarly, we can also generalize this to Q-learning with linear function approximation. You can also write down the associated O.D.E for this Q-learning with linear function approximation. And this, again, is an affine switching system. And this is controlled by some switching signals that depends on, again, your parameter theta t and the corresponding like greedy policy, right? And as we can see that if this switching system is asymptotically stable, then this leads to the convergence of Q-learning with linear function approximation. But this is not always like, but you cannot easily actually prove, because we know that even in general, Q-learning with linear function approximation may not necessarily converge. And based on sort of the stability result we shown earlier for the linear switching system, we can immediately construct what are the sufficient conditions for the system to be asymptotically stable. Say, for instance, if this matrix here is strictly negative row dominating diagonal matrices, then this will be asymptotically stable. And this basically leads to this new sufficient condition we constructed. And we shown that this condition is strictly less conservative than the Manos condition under the same assumptions. And we can easily actually construct a lot of examples that satisfy this sufficient condition, but that fails to satisfy the Manos condition. So to some extent, this is also intuitive because the Manos condition is based on constructing some Neapolo functions for the nonlinear systems, right? Whereas here we're using some necessary conditions for proving the stability for linear switching systems. So that's why we have these tighter conditions derived. So that is what I want to talk about Q-learning variations. And I think sort of the picture is clear for now. And I hope that you are able to actually walk away from this talk, being able to derive the proof for Q-learning algorithm convergence and or even any other of your favorite Q-learning variation. So the idea is essentially you write down what is the Q-learning or other algorithms, and then you find out what is the associate nonlinear O.D.E, and this oftentimes will become a affine switching system, and using the sandwich result we shown earlier, you will be able to establish convergence. So that is sort of the main idea here. And I think surprisingly to me, I checked a couple of quite some literature, and I think this is indeed the first connection between reinforcement learning and switching systems. Although both of those two topics has been extensively studied in different literatures, but surprisingly, nobody have ever established this connection, although it looks quite natural to me. Because literally, like you can see that Q-learning is just a affine switching system. And also, I think the proof, like based on just applying the Ball-Cross theorem, we can see that it's extremely simple and very intuitive, right? There is very minimal effort you need to pay for it. You just check a bunch of conditions and you're done. And this can be easily extended to many other co-learning variants and provides tight bounds in some cases, and I think tight conditions in some cases, and I think that's also quite interesting. And as for future work, of course, it will be interesting to also analyze what are the discrete time dynamics of those switching systems in order to generate the convergence rate and also hopefully get much tighter error bounds for those algorithms. And I think this type of control theory can also help us to inspire us to design what would be a more efficient way and a robust algorithm for reinforcement learning, and how we can actually design those feature matrix to satisfy certain conditions to ensure stability. So those are, I think, very interesting future topics that we will investigate. And with that, I want to maybe take the next 10 minutes or so to move on to the second part of the talk, which is related to double Q-learning. And as I said, this again also falls under the same umbrella of dynamic system perspectives. And we all know that double Q-learning has been widely used in deep RL implementations in practice. And a lot of numerical experiments shown that this actually outperforms Q-learning in many experiments. And this work here, we're trying to really just make a theoretical comparison between double Q-learning and Q-learning, and trying to understand why it works and when it works. So just a quick review of what is double Q-learning, as we discussed earlier. Also here, we're going to mainly focus on linear function approximation case. So the double Q-learning basically maintains two separate estimators, right? Theta A and theta B. And those two are updated in a sort of asymmetrical fashion, right? We use the estimator theta B to sort of evaluate the target values here, right? We use theta A to evaluate the target values here. And we use sort of the greedy policy under theta A to generate samples here, and use the greedy policy here to of theta B to generate actions here. And what's different, so in the original double Q-learning, actually there's also this additional random variable beta k, which is an IID Bernoulli random variable with probability 1/2 to be equal to 1 and 1/2 equal to 0, meaning that those two updates are randomly picked at every iteration to be updated. Okay. And I think based on also Aditya's talk in 2 weeks ago, like I think we all have a good idea that I think the choice of step size actually matters a lot. Not only affects the convergence rate, but also affects what is the asymptotic variance of those algorithms. So in order to make a fair comparison between those two algorithms, so what we decided to do is let's just fix the step size delta k for the double Q-learning to be twice as large as the step size of Q-learning. So by setting this to be twice as large as the step size of Q-learning, we can make sure that those two algorithms actually have the same transit behaviors and have the same convergence rate. And then all it left is to compare the asymptotic variances of those two algorithms. So here is basically a very one of our main results that we shown in the paper. So basically, if we set the step size for Q-learning to be this 1/k, right, up to some constant g, and we set the step size for double Q-learning as twice of that of the double Q-learning, then we can show that if you look at the asymptotic mean squared error of double Q-learning, is actually strictly worse than that of the asymptotic mean squared error of Q-learning. So meaning that it seems to sort of suggest that double Q-learning is not necessarily always going to be better than Q-learning, because it suffers from a higher sort of variance in the end. And this higher variance can be mitigated if we look at the average estimator, right? If we take the average of those two estimators and look at the asymptotic mean square error, we can show that that is going to be exactly the same as the asymptotic mean square error of Q-learning algorithm.
Right. Can I ask a question, or like somehow maybe just represent what Hado would say, the inventor of Q-learning? I think that these guys were after the bias, and then there is an understanding that the bias goes away asymptotically, so it like asymptotically, yeah, okay, double Q learning is not going to gain you anything. I'm not necessarily saying that I subscribe to the camp who believes in double Q learning, but that's the argument, right? So that the bias due to the presence of the max is somehow being reduced because use these 2Q functions. So what's like, I guess this is fine. Like I think that they would say that, yeah, okay, we agree. This you can do asymptotically. This is how it's going to be, fine. But like, isn't it more important to look at the bias?
I think that so the bias would make a huge difference at the initial stages for sure. Not maybe, as you said, like asymptotically, the bias will essentially go away and it would not affect too much. And I think the way, like, how to interpret here is really that I think the choice of step size really makes a huge difference. And oftentimes in practice, I think a natural attempt is to use a very large step size for double Q learning. So that you can reduce the bias at the very beginning very fast, and the algorithm actually converges fast at the very beginning. But we should also, like, if you are also interested in the optimal policy, like in the end, so maybe we should also like take into account of sort of the increased variance caused by increasing the step size, and I think that the bias and the variance, both of those are sort of integrated in this mean squared error here. So this sort of like reflects both of them.
Yeah.
In a combined fashion, in some sense, yeah.
Right.
Okay. And I think this type of observations we have from the theory also aligns a lot with the numerical experiments we did, right? So just to give you an example, here's like the popular Bayes example where we compare with like we compare to Q learning. Say for instance, Q learning here is the red curve, and we compare to we also like draw the curve for double Q learning with using the same step size. We use the same step size as Q learning, then double Q learning actually converges much slower than Q learning, which is sort of as expected. But if you're using twice as large as the step size, then you see that Q learning, like double Q learning, actually converges with nearly the same rate as Q learning. However, it has a much larger variance in the end, like the mean square error is much larger than that of the, so that is the, I think that is the black curve there is larger than the red curve. But if we look at the average estimator, actually like the mean square error of double Q learning becomes very similar to Q learning. So this is for this example. In other examples, we see that actually double Q learning can be even faster than Q learning, right? With using twice the step size. If you use the same step size as Q learning, it's worse than Q learning. But if you use twice as large as the step size, then double Q learning, which is a black curve here, converges faster than Q learning. And eventually it also has, like if you output the average estimator, it actually has also a smaller, which is the green curve here. It also has a much smaller variance in the end.
So
I guess
like why is this happening?
So I think this is sort of aligns with what we discussed here, right? So the average estimator has a smaller variance comparing to if you randomly update either of those estimators. And those estimators have a much larger variance than the Q learning algorithm.
Well, it's never said that it's going to be better. Double Q learning, it just predicts that in the limit they are the same.
I think in some of the existing like studies, people say that this helps to find a better, like double Q learning to observe that this finds better policies in the end, especially when you use nonlinear function approximations.
That's true. I'm just trying to understand the experimental results here. Yeah, like the next graph, when you say that like it can even be better, then I'm like, okay, like I didn't see that coming. Why is that?
Yeah, that's also something we are not able to actually explain very well why actually, because theoretically speaking, like if you use twice as large as a step size, we've shown that actually the transit behavior should be similar.
So maybe if you just run it longer, then like it's gonna be the same, but it's a transient advantage that, and it would,
Right.
or maybe it's a numerical issue with the Q-learning, but I don't know, like, but like it's weird.
Yeah, I think the theory only says more about the asymptotic performance, and the transient behavior. I think that's also, I think it's also quite surprising to me. Like even from the very beginning and till the very end, I think double Q learn. Actually, if you look at those, if you compare double Q learning with Q learning here, yeah, it's actually much better. Like from the beginning to the end. So it's hard. It's actually, yeah. I don't have a good explanation.
I'm wondering about whether this is asymptotic or not. But the red curve is coming down, so I think that it's catching up. So maybe if you would continue the graph, it would catch up, but it's just like a slow start. Yeah.
Yeah, it could be because here it is catching up eventually. Yes.
Right. So maybe this these figures show the transient advantage that people have been quoting before. Yeah, it's the advantage of double Q learning. By the way, shouldn't we go for triple Q learning then? Like if double Q learning is better than Q learning? Then...
So yeah, I'm not sure use the triple estimator.
Sorry, I got a quick question regarding this choice of the step size. So if you know that Q learning is stable for a certain step size, do you know that double Q learning will also be stable for double that step size, or maybe that can be actually unstable?
So that's a very good question, and we should admit, first of all, the convergence for double Q learning, even in the linear function approximation case, is unclear, right? So we know that there is like we also the Mellows condition and what we discussed earlier provide some sufficient conditions for Q learning, like what step size and what features would make it converge. But there is not a corresponding theorem for double Q learning yet. So our results are based on the assumption that both of those converges.
Right.
And whether like you can have making twice as large of step size would still guarantee the same sort of conditions is unclear. Yeah.
I see. All right. Yeah. Thank you.
But it seems like in practice, when you double the step size, it seems to always work.
All right.
I guess the takeaway here is really that one should be cautious when implementing double Q learning. It's definitely not the larger step size, the better, right? And we should maybe try to also make a better balance between the trade-off of the bias and the variance terms if you want to get the best out of it. All right, I think I want to maybe just make a final remark here that I think, of course, reinforcement learning is not just about optimization and control, but I think a lot of the existing optimization control theory can definitely help us to gain better understanding of reinforcement learning, and hopefully there will be more work in this direction, and we will be able to bridge the huge gap between the theory and the practice. And with that, I want to also maybe shamefully use this as an advertisement for the upcoming seminar by Sean, like I think in 1 hour. And this is a talk for the mathematical foundations for data science online seminar that I'm co-advising with a couple of other colleagues. And if you are, and I think this is also closely aligned with the theme of theory of reinforcement learning, and many of the audience here might be interested in this one, and feel free to join this seminar if you are interested. Yeah. All right. Thank you very much.
Yeah, thank you. Grab a quick snack and then enjoy the next talk. It's kind of a stream of talk.
Yeah.
I just had a quick question.
Sure.
And thank you. I enjoyed the talk. Thank you very much. Were you able to do it like a Lyapunov equation analysis to compare double Q and Q? Maybe that's where I mean, that's how you got the variance, right?
Yes, that's exactly what we use, using the Lyapunov equations for both Q learning and double Q learning, yes.
But so then doubling the weight, you know exactly how it impacts the variance. So it's not just that, it's just the transients. Is that what you're saying? I guess I didn't quite understand. So the doubling the gain could hurt the variance. Was it hurting the variance and helping the transients, or vice versa?
So double the step size would hurt the asymptotic variance, but help with the transient behavior.
Yeah, we need a theory to bridge the two. It's crazy. Yeah.
Right. I guess the point here is, like, if you consider the average of the two estimators, it doesn't really hurt the asymptotic variance, and then you can maintain both good transient behaviors as well as more variance.
Right.
So I guess when you implement double Q learning, you should output the average of the estimators. Yeah.
But D.T. and I had such bad luck with Goupert-Polyak averaging. It tended to give us terrible transients. Yeah. Anyway, interesting.
Yeah, and I should also say that most of this result only holds true for linear function approximation, and it's unclear whether this result will be extended or can be extended to the nonlinear function approximation case. So a lot of the observations people observe in practice may not necessarily apply to here, because those are like based on neural networks. And I think also, like, speaking of, there are also many other ways you can maybe, like, instead of using this double Q learning, also maybe Polyak averaging, and as we can see that earlier, we have this in the averaging case, we put this delta here, trying to sort of push those theta A to be the same as theta B, in some sense, to control or to have this correction term here. We can do the same thing for double Q learning. Actually, we can put also like a additional correction term here, sort of as a regularization to make sure theta A is close enough to theta B at every iteration. And if we do that, we've shown actually in the theorem that the larger theta, like the larger those delta is, then the smaller the variance is. So actually using a larger, like, correction term actually helps to reduce the variance.
All right, so I think we got a bunch more questions in the pipeline as well. So maybe let's just go in order. So Ahmed Tuati, can you ask a question if you're here? Can you mic?
Yes.
Are you still here, Ahmed? Oh, he disappeared. But anyway, I'm just going to read his question, and then maybe he's going to tell you if he's satisfied. So he's wondering about how the sufficient condition for linear function approximation was derived. Can you say a few more words about that?
Right. So the sufficient condition here is derived basically by letting this matrix here to be strictly negative row dominating diagonal matrix. Right. Remember that is sort of the sufficient and necessary condition for asymptotic stability for linear switching systems here.
Right. So basically,
that
condition that you have implies the condition that you have in mind. But maybe is there like something simpler?
It does make if A sigma by themselves are negative row dominating diagonal matrix, then you immediately get the symptotic stability here. So I see
I'm
that
gonna have to ask Ahmed if he's happy with this.
I see the similar bottleneck as the Manos condition is that it's very hard in practice to check those conditions, whether they hold true or not.
Yes.
So
Sorry,
the
sorry, I had the
next,
problem with the mic. Yeah, sorry for that. So yeah, so you're saying that the sufficient condition is derived from the fact that we have to have a negative row dominant diagonal matrix. Okay. Okay. Fine. Thanks.
May I ask a follow-up question?
sure. Yeah.
Sorry. Let's just go in order because we've got like a couple questions in the pipeline.
Oh, okay. Sorry.
So we're gonna get back to you, okay? Because I'm just reading a few from the chat. So Sharan Waswani had a question. Sharan, are you here?
Hi, yes. So in the sandwiching, do we know if the gap between the upper and lower bounds monotonically decreases? That would be a good property to have.
So the sandwich result is basically provides an upper bound and lower bound. I'm not sure what do you mean by monotonically decreasing. So basically what we've shown is that the whole trajectory xt is going to be, if we look at this result here, so basically we can show that the qt of the q-learning algorithm is going to be less than some upper bound of qt bar and less lower bounded by some qt underlined there, and there is not we are not able to quantify exactly what is the gap between those two.
Yes, but just saying that the gap is monotonically decreasing, that it cannot increase as k increases, because as k tends to infinity, it goes down to 0. But if you have some monotonicity, we can like say something for an intermediate k.
I guess we didn't prove that part, and I'm not sure whether that is always true. But that's definitely an interesting question to think about. Yeah.
All right. Okay. Thank you.
All right. So next up, we had a question by Kishan. Kishan, can you ask your question if you're a mic?
Yeah. So in slide 27, the sufficient condition. So right now it's strong because it needs to be satisfied for every policy. So is there any relaxation so that we need to satisfy this condition only for an exploratory policy? Like since we are following pi of theta p policy to collect the samples. So is that condition enough? Any
So I guess if you know like what the structure of the optimal policy, then you can always use as a relation.
Okay. Thank you.
All right, and maybe, yeah, so we had like a couple comments in the chat by Björn Winkler. Maybe you can ask a question or comment rather. No, okay, well, maybe I'm just gonna ask. It's like some people are saying in the chat that this connection between switching systems and Q-learning has been pointed out previously in the literature. So one reference that Björn is pointing out is a paper by Wunder, Littman, and Babes. It's called Classes of Multi-Agent Q-Learning with Epsilon Greedy Exploration. So like, do you know about this paper, and can you make a comparison between your perspective and theirs?
So I'm reading at the paper. Let me see. I wasn't aware that this paper is about using switching systems to get the convergence of multi-agent flow learning. But yeah, I will probably read this paper first, and we'll
Yeah, right. I guess like nobody expects that you're gonna have an opinion
Thanks
based
for
on
the
just the title. All right, so I'm just scrolling through the other questions. So Ibrahim Al-Shar, can you ask your question if you're here? Oh, we have a bunch of shy people today.
Or maybe microphone not working.
Yeah, a lot of technical issues.
Can you hear me now?
Yes.
Oh yeah.
Oh, great. Okay, so it was mostly a remark about this paper. I just wanted to point. I think Niao, you said something about this thing about Q learning being a switching ODE, that you hadn't found it in the literature. So it was just to help point you in the direction that it has been in the literature for a while. And I think people in games theory has been doing this kind of stuff since like the 80s or 90s, but not on Q learning in particular, but lots of other related type of systems.
And
but
so you know this
is not at all in the same level as what you're doing here. It's just it's a different thing, something for you to look at maybe.
Yeah, this is definitely interesting, and thank you so much for pointing it out. Yeah.
You're welcome.
Siva, would you like to ask your question now? Siva Magaluri? You here still? Okay, maybe not. Were there any other questions that people had? Or do we want to?
I had a question. Okay. So the feature space currently is fixed, right? So the linear function approximation. So are there any results parameterizing the feature space itself? Like in general, we actually search for if we take RBFs to be some feature space and try to find the optimal scaling parameters and so on, then that would be better than rather than fixing the feature space a priori for an environment. So do you have any comments regarding that?
I think that's a very interesting topic, like trying to learn what are good representations, right? And sure, this is closely related to the conditions for the stabilities, right? For certain features, like it leads to more stable systems, and for other features, it may not, right? And I think like how to learn those features in a proper way might. Like there are definitely many ways you can define what are good features, right? I think taking into account the stability conditions is maybe one interesting direction.
Okay. So, but the current analysis won't work for the feature space which we have already parameterized, is it? Like here in this sufficient condition, let's say I am parameterizing this phi ice. So then that won't work, is it? I mean,
so I think the result holds true for general feature mappings, but like if there is a particular structure there, and you basically just have to plug it in and see if it holds true, and that might lead to new conditions, specifically customized for the parameterizations you have.
Okay. Yeah. Thank you.